Hey, good morning. I'm going to work an inverse kinematics example. Okay, let's start with this serial robot. The first one we have, it's a 3-degree of freedom planar robot. We have 3 links. We have the forward kinematics are solved here for us. And we have, in this case, we're going to solve the inverse kinematics. We're assuming we're giving a consistent and desired pose. When I say that, it means it's a pose, a position orientation that's consistent with the robot. In this case, it's only a 3-degree of freedom robot, not a 6-degree of freedom robot. So I can't artificially I can't arbitrarily fill out all of these 12 parameters in this, but that's what's given. So I have all the kinematics. Those are my first steps. I'm going to define the wrist center. And the wrist center is at PC. I see that this is a 3-degree of freedom robot working in a 2-dimensional space. So the first 2 joints are going to position. The last joint's going to orient. That makes that the wrist center. I have to define the wrist center from the givens, and I'm going to set it equal to the wrist center that I get from the forward kinematics. Those are expressions. On the left-hand side from the givens, I'm given the position orientation of frame 3. Position of frame 3 is here, X, Y, Z. That was from the that was right here. And then I see I have to back up in the direction X3 by a distance. In this case, it would be L3. This is distance L3. So I have to back up a distance L3 in the X3 direction. The X3 direction was row 1, column 1, row 1, column 2, row 1, column 3 from the givens. I'm just going to pull those together and kill X prime, Y prime, Z prime, just so I don't have to carry that around. That's what I have. So those are known values. Of course, I'm not putting in numbers, but those are known values. On the right-hand side, I have to have the position of frame 2 in terms of expressions. They come from the forward kinematics. So I have to go to the last column of T20. That gives me the position of frame 2 from the forward kinematics of the expressions, and I'll write it in here. It's L1 C1 plus L2 C12, L1 S1 plus L2 S12, and then 0. Now, again, I said the X, Y, Z's and the R's can't be arbitrary. In this case, you can see that Z has to come out to be 0. That doesn't solve anything for us. Our unknowns are theta 1 and theta 2, so I need to solve for those 2. Let's do that. I'll jump over to my common solution techniques. Look for any one equation, one unknown. I don't see that. I've got 2 equations tucked in with unknowns of both theta 1 and theta 2. Kind of complicated there. Don't see an easy solution. So I think on common solution technique number 3, I said square and add. So let's go ahead and try the square and add approach. So I'll square and add both equations. So on the right-hand side, I get x prime squared plus y prime squared. On the right-hand side, I'm going to get this whole thing squared plus this whole thing squared. So I'm going to look at terms. So I'll give me an L1 squared, C1 squared plus S1 squared, which goes to 1. Just becomes 1. I'll get an L2 squared, C12 squared plus S12 squared, which also Pythagorean identity goes to 1. And then finally, I'll get a 2 times L1 C1 L2 C12 plus L1 S1 L2 S12. So I get all this. If I look at this, plus 2 here. If I look at this term right here, I can pull out a 2 L1 L2 times C1 C12 plus S1 S12. Good luck seeing it, but it's what we're practicing doing. Do you see the angle addition identity tucked inside there? This was like cosine alpha, cosine beta plus sine alpha, sine beta. That would become what is that? Cosine alpha, cosine beta plus or minus. What's going on with my camera? Spooky. Sorry, my camera's going crazy. Ignore that. But I can see that this becomes cosine theta 1 minus theta 1 plus theta 2, which gives me cosine minus theta 2. Cosine minus theta 2 is cosine 2. So this becomes cosine theta 2. All right. So I did the angle addition identity. I substitute everything and I get this. So I get x prime squared plus y prime squared equals L1 squared plus L2 squared plus 2 L1 L2 cosine theta 2. And I can solve that for theta 2. You know, this is the, I think, is this the law of cosines? Yeah. Yeah, I think that's just the law of cosines. It's funny that this stuff shows up. I say it's funny, but it's not really. It's just geometry. It's kind of showing up in different ways. It always surprised me that it works out this way, but it does. So I'm going to solve for theta 2 as the inverse cosine of x prime squared plus y prime squared minus L1 squared minus L2 squared all over 2 L1 L2. And that'll give you two solutions for theta 1 for theta 2. Now I've got to go back and solve for theta 1. This point, you know, at this point I have I know theta 2. I can expect, you know, I've now got two equations, one unknown. It's going to be a little easier. This one's still a little bit messy. It's funny for this little 2-degree of freedom robot or 3-degree of freedom robot. You know, there's a little bit of math here. I'm going to take those two equations now and expand them out. So that would give me x prime equals L1 cosine theta 1 plus L2 cosine theta 1 plus cosine theta 2. So that was cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2. Because that's what cosine 1, 2 is my cosine theta 1 plus theta 2. And then y prime is L1 S1 plus L2. Sine theta 1 plus sine theta 2 is sine theta 1 cosine theta 2 plus L2 sine theta 1 cosine theta 2. I'm going to combine these things. This is going to give me a L1 plus L2 cosine theta 2 cosine theta 1. It's going to give me a minus L2 sine theta 2 sine theta 1. This will give me an L1 plus L2 cosine theta 2 sine theta 1. And this will give me a plus L2 cosine theta 2. I made a mistake here. Sine theta 2 cosine theta 1. Okay. And so here I've got, if I call this term A, if I call this term A and this term B, I can see that it's of the form on the common solution technique here. I got A cosine minus B sine, and yeah, A cosine minus B sine, and A sine minus B cosine. So that gives me that the solution is theta A tan 2 y x b comma A. So that can give me the solution for theta 1. So I suit common solution number 8. Common solution technique number 8 says that theta 1 is now A tan 2 of y prime comma x prime minus A tan 2 b comma A. Did I do that right? Okay. And that's one solution. All right, give me just, okay, got one more part. I'm recording this first solution real quick before class starts. Okay, now let's go to the second part, part 2. This is the wrist part. And here I need to solve for theta 3. So again, I'm going to get the wrist from the givens. I'm going to get the wrist description of the wrist. And for the wrist, the description of the wrist is in the projection of the wrist back onto the arm. In this case, the wrist is frame three. The arms ends with frame 2. So it's a projection of 3 onto 2 from the givens. And I'm going to set it equal to the projection of 3 onto 2 from the forward kinematics. To get 3 onto 2 from the givens, I'm going to say it's, well, R2 onto 0 inverse times R3 onto 0 from the equals then R32 from the forward kinematics. So R2 onto 0 inverse, I'm going to take, the projection of frame 2 onto 0 right here. I'll put in the known values of theta 1 and theta 2. Okay. I'll then take the inverse of that. I'll multiply by the R30, which is right here. And that'll give me, in numbers and numerical values, will give me a set, and I'm going to call them prime. So R11 prime, R12 prime, R13 prime, R21 prime, R22 prime. I see my ones don't look that good, so on. And then from the forward kinematics, I need projection of 3 onto 2. I don't have it here, but I can see it'll come from the transformation of 3 onto 2, which is this row. And since my alpha is 0, it's just rotation around the z. So I know that'll look like cosine theta 3, negative sine theta 3, 0, sine theta 3, cosine theta 3, 0, 0, 0, 1. And now I'll solve, and I will use these two equations to solve. Since I could just take any one of those equations and say theta 3 is the inverse cosine of one term or the inverse sine of a term. But since I have more than one piece of information, I'll use my a tan 2 function to get a unique answer. So theta 3 is going to be a tan 2, and I'll do the sine part. So the sine part is R2, row 2, column 1 prime. The cosine part is row 1, column 1 prime. And that gives me one solution. Okay, now let's pull it all together. So for theta 1, I got one solution. For theta 2, I got two solutions. For theta 3, I got one solution. I multiply all those together. So 1 times 2 times 1 is 2 total solutions. There's 2 total solutions. And there's 2 total solutions to this guy. And they would be is here as I squared them. All right. With that, I'm going to end that example. Let's see here. Let me figure out how do I do this? Just stop sharing. Okay. Whew. I am stopping the recording. I was trying to record an example.